To introduce you to oscillation, I'm going to give you just an example. We're going to talk about this. Let's just say we have a bowl, and let's just say we take a marble and we put it in a bowl. Well, when the marble is at the bottom of the bowl, nothing's going to happen, and this is actually what we call equilibrium. It's equilibrium because, to put it in a non-scientific term, the marble's happy. It really doesn't want to go anywhere. But if you were to take this marble, if you were to actually move it up, and if you were to put it, let's say, towards the top of the bowl and let it go, we know that the marble is going to roll down the bowl. In fact, it's going to roll up here, and then it's going to roll back. And in fact, if we were to ignore any friction, if we were to ignore any air resistance, this marble would just continue moving back and forth and back and forth. That's what an oscillation is. An oscillation is its repetitive motion. So the marble wants to just keep moving back and forth. So it's going to pass equilibrium, go to the top, then go back to equilibrium, pass the top, and so forth and so forth and so forth and so forth. And again, if we ignore any type of a restrictive force, it would keep going on forever and ever and ever. Now, it's important to understand a couple of things with this. First of all, when the marble is at the top, the reason it wants to come back to equilibrium is because of the force of gravity. We have gravity that's trying to pull it down, and so it's going to continue to go back to that equilibrium position. In this case, that force of gravity that's acting on it is what we call a restoring force. The restoring force is a force that is moving to that is going to act to move the object back towards its equilibrium position. So a restoring force is typically one of the forces that we will look at. So force of gravity is a restoring force on the marble. If we're looking at a pendulum, force of gravity is also a restoring force on a pendulum. If you had, let's say, a mass on a spring, you could have a spring force be the restoring force on the mass that's attached to the spring. So there's different types of restoring forces, but it's really just one of the forces that we're looking at that's causing that restoring force. So a restoring force is causing it to move back to equilibrium. So we have a restoring force on this side, we have a restoring force on this side. Really anywhere in between, we have a restoring force that's acting to move the marble back towards equilibrium. Now, the other thing that's important to understand when we're looking at oscillation is the period. The period is the time it takes to complete one full cycle. So if we're talking about our marble, the period would be the time it takes, if I were to bring it over here to the right, at the top, and let it go, the period of the marble would be the time it takes to go down, up to the top on the left, and then back down and up to the right again. So the full cycle is back to its original position. So that's what the period is going to be of our oscillation here. So the period of the marble. Now the period is measured in seconds. It's a time. Okay, so it's important to understand that. Now, in addition to the period, we also have the frequency. The frequency is not the time it takes to complete one full cycle, but it's the number of cycles per second. So if we look at how many cycles we have every second, that's going to be the frequency. Now the frequency is actually measured in hertz, which we abbreviate Hz. Now it's important to understand the relationship. Because the period is the time it takes to complete one full cycle, so basically the seconds per cycle, and the frequency is the cycles per second, the two are inverses of each other. So the period, the variable we're going to call t, the frequency, the variable we're going to call f, they are inverses of each other. So frequency is equal to 1 divided by the period is equal to 1 divided by the frequency. So when you're looking at hertz, the other way to indicate hertz is actually 1 over seconds. So 1 hertz is actually 1 over second. All right, so it's important to understand the relationship that we have between these two. As we go on, this is going to be important for oscillations. It's going to be important for simple harmonic motion. It's also going to be important for waves when we get to waves.